So what it is the following. Let's see. It's given. We came across associated Legendre differential equation when we solved Helmholtz equation in spherical coordinates, but it is sort of similar. Alright, so this is Legendre differential equation where the independent variable here is z. Okay, y prime is dy over dz. So we are seeking solution of this differential equation, and we want to find this solution not in infinite domain but in this regime. Z lies between -1 and +1. I'll tell you why what we are doing. So given this differential equation, what can you tell me about P of z and Q of z? What is P of z?
2z minus 2z.
Negative 2z over?
1 minus z.
Yeah. And Q of z is? Okay, L is any real number. And we'll see when it becomes integer what happens to it, okay? But L can be any real number. Yeah, I mean, P of z at z equal to 1. Okay, at z equal to 1 and -1, it blows up, right? I mean, but z times P of z at z equal to 1 is what? Z minus 1 times minus 2z over, I'm going to write it as z minus 1 now with a negative sign, times z plus 1. Okay, so I can cancel these things. So at z equal to 1, what we have is, this is 2, so it is 1, right? So minus and minus sign can be cancelled, 2 and 2 will cancel, and z equal to 1 will be 1, okay? So this is what we called as what in the initial root, I think s of z or something like that, right? That function was s. So s of z at z equal to 1 is 1. Fine, that exists. But what I'm going to, at z equal to 1, similarly, you can see it has got singularities, and we can eliminate that, and all that stuff is there. But I am interested, yes, this differential equation at z equal to +1 and -1 will blow up. But I'm not interested in the entire regime. Let us say I'm interested, let me just say, I'm interested in this regime, okay? So what about P of z at z equal to 0? How does that behave? P of z at z equal to +1 or -1, obviously it has got singularities, okay? I mean, and I think I'm pretty sure z squared times Q of z is also fine. But what about z equal to 0? If you want to check, you can check that, okay? The behavior at z equal to +1, what happens to it? You can check what happens to it. In general, if it is infinite domain, we have to consider, we have to do the expansion around z equal to 1, all right? I mean, but I'm interested in the solution in that regime, and I'm also supposing I want to do the expansion about z equal to 0. So I need to find out what z equal to 0 is. What kind of singularity do I have? Is it a singular point, ordinary point? We have to classify P of z at z equal to 0. So what is happening to P of z at z equal to 0? Is 0, right? So Q of z at z equal to 0 is simply L times L plus 1. So this is finite, and this is also finite. Okay. So what I'm going to propose is, then if z equal to 0, P of z and Q of z does not blow up, and I'm interested in the solution in this regime, what kind of a solution can I propose for this differential equation? If I want to do the expansion around z equal to 0. Remember, the way we write equations are like this, right? I mean, I have to decide whether I have to write it like this or z to the power sigma, Frobenius series or ordinary power series. I have to decide. Okay. Now I'm expanding around z naught equal to 0. So this is a solution I want to propose. Okay. Is this point clear? So I'm proposing ordinary power series, not Frobenius series, generalized power series, as a solution of this differential equation, mainly because I am interested in the solution in this domain. Okay. The reason is sometimes z is actually in quantum mechanics is cosine theta. Why I can do that is, and cosine theta is always between -1 and +1 in that regime. Okay. So because of that, the interesting solution for me is only in this regime. Okay. So that's why I'm restricting to this. I'm not even worrying about Frobenius series. Okay. I mean, there's some other reason why we are this subject to, I mean, in this regime. So this is also important. Solving the differential equation, not in infinite domain, but in this domain. Okay, so so that's also important for proposing. The starting point has to be correct. Okay, so I'm proposing ordinary power series as a starting point for the solution of the differential equation, and I have to find these coefficients using recursion relationship. I mean, then the rest is easy. Okay, so watch for what the problem states, which are infinite domain, or so we don't have to make a problem more complicated than what it is. Okay, otherwise I would have put z minus 1 to the power of n, all that stuff, right? I mean, so what I'm saying, although they're blowing up at z equal to +1 and -1, it is finite at z equal to 0. So I'm going to propose ordinary power series. Okay, so that's essentially what I'm trying to say. All right, so let's do this. Y prime of z is then nothing but a sub n, n z to the power of n minus 1, n going from 0 to infinity. Y double prime z is a sub n, n, n minus 1, all right. So let's start substituting all these things into our differential equation. 1 minus z squared, and y double prime is here. A sub n, n times n minus 1 z squared, n going from 0 to infinity, minus 2z y prime. Y prime is a sub n, n z to the power of n minus 1, n going from 0 to infinity, plus L times L plus 1, a sub n, all right. So I'm just substituting all these things into my differential equation. All right. You make any mistake? Oh, n minus 2. Sorry. Yeah. Yeah. Okay. Minus 3 y prime is e to the power n minus 1. Okay, fine. All right, so here we got two terms. So we can write this as what? Summation a sub n. The first term is n times n minus 1, z to the power n minus 2, okay. Negative a sub n, n minus 1, z to the power n, because this is z squared, minus 2 times a sub n, z to the power n, plus L times L plus 1, and going from 0 to infinity, a sub n, z to the power n equal to 0. Right. Alright, so that's the first term, and minus z squared is there, so I took it, yeah, okay. Alright, so what is the recursion relationship? What should I do to get the recursion? Somehow we have to find a way to calculate a sub n from the recursion relationship, so we have to set that up. So should we look at the coefficient of z to the power n in this whole thing? So if you want to look at the coefficient of z to the power n, what's happening? The first term, here we have the power z to the power n minus 2, right? So the infinite series, so the term that I'm looking at somehow is n going to n plus 2 will have z to the power n. So if I change the coefficient n to n plus 2, that is the term which will have z to the power n. All right. So it will give me the following equation: a sub n plus 2, n plus 2, n plus 1. Okay. That should be equal to, I'm going to take all of them to the other side. I don't have to change anything. A sub n, n times n minus 1. Okay. That become 2n. Right. I'm looking at the coefficient of z to the power n. And then the last one will be negative L times L plus 1. All right. So I'm transporting all this to the other side, right hand side. So that will become plus, that will become plus, and that will become negative. So this will give me a relationship between a n plus 2 and a n, and that will give me a recursion relationship. I'm going to write down here. So what I have is a over n plus 2, a of n plus 2 over a n is nothing but, this is n square minus 1 plus 2n. So these two, so n square minus n plus 2n is nothing but n plus, okay. So what I have is nothing but n times n plus 1 minus L times L plus 1 divided by n plus 1 times n plus 2, right? Is this clear? All I've done is looked at the coefficient of here. Okay. This has to be satisfied for each power of z, z to the power 0, z to the power 1, and so that leads to the following recursion relationship. Okay. All right. All right. So that's what we had. So from here we had to calculate, somehow calculate a n, right? All right. So it's an ordinary part series. In ordinary parts in series, there's no condition on a naught. In generalized power series, we had a naught should not be equal to 0, right? We don't have that restriction here. Okay, that's important because if I put a naught equal to 0, it gives me two independent solutions automatically in this case. You know, one will be odd series in Z and the other one will be even series in Z because of that condition. So we don't have additional restriction on the coefficient A0. So we could choose one solution as where A naught equal to not 0, A1 equal to 0, and the other one is A1 equal to 0. Did I say that? Okay. I don't know what I said. Let's see. We can choose one in which A naught equal to 0 and A1 equal to 0, right? The other set of solution, independent solution, we can get by that, okay? So this will give you solution Y1Z, okay? And this will give me another independent solution Y2Z. And I can find the coefficients somehow. So this is what we did in the harmonic oscillator case also, right? We could use two independent solutions of ordinary power series. But I cannot, this condition I cannot use in the generalized power series, okay, case. All right. So if I choose in the recursion relationship n equal to 0, then I have this A2 over A0 will be n equal to 0. So I have minus L times L plus 1 divided by 2, right? So n equal to 0. So how do I write? So my first solution, if I go with that case, what do I have to calculate, right? So in general, it is nothing but A naught plus A1 Z plus A2 Z squared. It's an infinite series like this. And if I make A1 equal to 0, right, because of the recursion relationship, A3 is something multiplied by A1, and A1 is 0, so everything will be 0. So all these coefficients, all these terms will, all the odd terms will disappear for the case A naught equal to 0 and A1 equal to 0, right? So all I have to calculate is only the ratios of the following coefficients: A2 over A0, Z squared plus A4 over A0, Z to the power 4, and so on and so forth. So that will be my first solution. Okay, first solution once I have calculate all these things. All right, so A2 over A0 is that, and this relationship will also give me what, n equal to 2. I will get A4 over A2 I can get, and from there I can get A4 over A0. So n equal to 2, so it is 2 times 3 minus L times L plus 1. 2 plus 1 is 3, 2 plus 2 is 4, okay? I'm writing like this because the tendency is to somehow make it 12, blah, 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 but then you cannot factorize it properly. So until you know what the form is, let's keep it like this and then try to start simplifying things. But what I need is not A4 or A2 for finding the solution. What I need is A4 over A0. So this tells me A4 over A0 is nothing but right, and that we have here, which is nothing but negative L times L plus 1 is A2 over A0 divided by 2, right? There is A2 over A0 is that, and then I have all these terms. Okay, I've got 2, 3, 4, which looks like a 4 factorial. Okay, so I'm going to put that inside here. Okay. so you can start seeing something developing, which is like 4 factorial at this point. All right, let's see what that looks like. Now let's simplify that further. All right, this is A4 over A0. So I need to plug that in there. And eventually I'll take A naught equal to 1. Okay, after all this, it's any constant, so constant times solution is solution. So I will make that as 1. All right, the first solution is then one. Where is that? I'm going to call that now 2 factorial. Okay. A4 over A0 is negative L times L plus 1. I'm going to call this 4 factorial. And what is this term? I'm going to write right now minus L squared minus L. What can I simplify that to? Can I call this minus 3L minus plus 2L, and then let's do that, yeah. So let's call that minus 3L plus 2L, okay? And then we can factorize it nicely. So what I have is then 6 minus L square minus 3L plus 2L is what I did. And I can, that will be L times L. I can combine these two and combine that two, those two things, right? So what I'll have is, if I do 3 plus L minus L times L plus 3, right?
Yeah.
Is it correct? Yes, so this is also L plus risk, right? Nice way. So this term inside the parenthesis is nothing but 1 minus L times L plus 1 over 2 factorial minus L times L plus 1, 4 factorial, and then this has become what?
L minus 2.
L minus 2, I'm going to make it as plus here, okay? L minus 2 times L plus 3, all right? Oh, sorry, I have forgot my z, important thing, function of z. That's my coefficient, this is z squared, right? And this is times z to the power 4. All right. So what I have obtained is the solution y1 is a even power in z. Case 1 is that, right? By putting that's your first solution. Okay, second solution you can follow the same recipe, except now we are going to put a naught equal to 0 and a1 not equal to 0. So that will give me my second solution. All right, so my second solution is then, so if a naught is 0, then a2, all the other even coefficients will become 0. So I can write this as the leading term is now a1z, right? N equal to 1 is the first term. The next term will be a3 z cubed, a5 z to the power 5, and so on and so forth. Okay, so I'm going to now pull a1 out. So the coefficients that I have to ratios of the coefficients that I have to calculate are a3 over a1 z cubed plus a5 over a1 z to the power 5, and so on and so forth. Don't stop at one, or at least calculate 1 or 2 coefficients, because then you can see the pattern of the functions most of the time. Okay, so because we also want, if possible, to convert the infinite series into a function if you can recognize the function. All right. All right. So my second solution is then, okay, I need to calculate all that stuff. Okay, we are going to take eventually a1 equal to 1 after you calculate the thing, and similarly a0 you're going to take 1 in that case also. Okay. So what is a3 or a1 here? Go back to that. So I'm going to put n equal to 1 here. A3 over A1 is nothing but 2 minus L times L plus 1, n equal to 1. Okay, that is A3 over A1. So this looks like a 3 factorial in the denominator. Okay, so I'm going to write this as 2 minus L plus 1 divided by 3 factorial. All right, so this a1 will take it as 1. I'm just writing this term right now. Should we further simplify this? Can we 2 minus L squared minus L over, yeah, we can simplify this also further, right? 2L minus 2L plus L, let us do. I want to write it in nice form. Okay, minus 2L plus L will be minus L, right? So what do I have? Minus 2 minus L squared minus 2L plus L over 3 factorial. So I have L plus 2 negative L plus 2 over 3 L plus L squared minus 2L, right? Which is nothing but 1 minus L plus 2 over 3 factorial. Okay, so I'm going to write this term as, I'm going to put a negative sign here because I want it as L minus 1. Okay, negative L minus 1 L plus 2 over 3 factorial z cubed. Is this clear? All I've just done is simplify, factorize that. I mean, if you just expand that, it should give you that, basically. I just showed the steps for you. All right, L minus 1 plus L plus 2 is nothing but 2 minus L squared negative L. All right. All right, let's calculate one more because these are, so this became, let me just write down this so that I don't lose it. Is negative L minus 1 L plus 2 divided by 3 factorial. All right. So the next term is A5 or A1 I want, but I will get A5 over A3 if I put n equal to 3. That's what I'm going to get. So 3 times 4 is 12 minus L times L plus 1. 3 plus 1 is 4. 3 plus 2 is 5. But what I need is A5 over A1. Okay, so I need that. So in order to get that, A5 over A1 is nothing but A5 over A3 times A3 over A1. So I have to multiply those two terms. So you can see the denominator has become what? 5 factorial, right? So at least that part we can do. But let's simplify. Before that, let me simplify this term. What is this term? I want to factorize it nicely. I'll multiply that, but in a way, let's get this. So this is 12 minus L squared minus L over 4 times 5. What should I do here? Can I do minus 4L plus 3L?
Yeah.
Will that help? Yeah. All right. So what is that?
L minus 3L plus 4.
Which
L
one?
minus 3L plus 4. Minus common.
What did you say?
Minus L minus.
Which ones are you combining? Should I combine this one first? That will give me L times L plus 3, right?
Yeah.
Okay. So if I did that, I get 4 is common. Okay. 3. I'm getting 3 minus
minus
L. This is okay. That's also 3 minus. Good here. Minus L. L. So that will give me negative L squared. This is minus 3. Is this correct? L minus 3 will be plus 3L.
Yes.
Okay.
L minus 3L plus 4. Fine.
Yeah, so it is 4 times 5. So I want to change one of them. I want it as L minus. Okay, let me change this then. Or let me change that. L minus 3 for one, that will be negative, right? So I'll have negative L plus 4, it looks like, times L minus 3 divided by 4 times 5. Is this correct? I made a negative here. So that because I want this is L minus 3, so negative was there. Negative, so it become L plus 4, L minus 3 is common. So, and I have a net negative sign also there. All right, so that is my A phi over A3, but what I want is A phi over A1. So A phi, actually there's a pattern here, we'll just come to that in a minute, okay? So what it is so denominator has become now 5 factorial, right? Because of 3 factorial, 4 and 5, and this guy has become this, all right? So negative and negative will cancel. There's a negative sign here. So I have L minus 1, right? I have a L minus 3. I have a L plus 2. I have a L plus 4 in this term, in the next term. All right? So this is positive. Now next term is positive, the coefficient. And I have what? L minus 1, L minus 3, L plus 2, and I have adding one more now, L plus 4, divided by 5 factorial, and then 0.5, okay, and so on and so forth. It looks messy, but I think it is now. Hopefully everything is correct. Let's okay, so what we have is, this is the odd series in odd powers of Z, right? Odd series in Z. So they are independent solution because, you cannot just go, one to the way by constant number. You have, the leading term here is Z, right? Yeah. So this is an infinite series. All right. So what did I say here in our Legendre polynomial? If L is an integer, what happens? What happens to the recursion coefficient? What happens to the series? Let's start with L equal to 0. Let's even say, simplest case. What happens when L equal to 0? So y1z and y2z are the two solutions of this differential equation, okay? So So what is happening to y1z when L equal to 0? If supposing my differential equation was this, okay, L equal to 0. Okay, that's what we mean by that, right? y1z is 1, right? All the terms are becoming 0. So an infinite series has become a polynomial. It terminates basically. It's become a polynomial. Okay, and the second solution, on the other hand, is an infinite series in Z, because L equal to 0, nothing is happening to this. One solution is a polynomial, other one is an infinite series, and hopefully, depending on, we may be able to look at when we expand for specific L's, maybe that infinite series we can recognize as some function also. Okay, so that's what is happening. Okay, so these are the Legendre polynomials. I'm just beginning to get the terminology polynomials and Legendre polynomials to you right now. L equal to 0. If L is equal to 0, y1z is nothing but a constant. Okay, but y2z is an infinite series. It is an infinite series. We can take n equal to 1, L equal to. We still have a series. L equal to 0 will become what? This is 2, negative 2, 2 over 3. Okay, 2 over 3 factorial, so it's 1 over 3, maybe it is something like this. Okay, so you can calculate the other terms. Okay, so this is what, but it's still an infinite series. Hopefully we can think about a polynomial solution, some binomial expansion, write something for it. So L equal to 0, this is negative 1 plus, okay, and this is 2, and this is 3 times 2, so 2 and 2 I can cancel, so I become, instead of factorial, it becomes that. I'm pretty sure the next one is z to the power 5 over 5. I'm not even calculated, but I think that's what will become. Okay, L equal to, you got a 3, 2, 4, 2, I think that's what has become. Okay, so it will be, the next term is perhaps this one. Okay, so fairly, you can just L equal to 0, you have a 3 here, plus 3, this is plus 2 plus 4, 5, 4, 3, 2, and so all other terms will go, and so I don't even have to calculate, it's alternating with the sign. I'm pretty sure the next one is simply minus z to the power.
First sign is positive or negative?
Which one?
Minus z cube.
Here? L equal to 0, this is negative, so that's also that's positive. Yeah. So it is positive. Yeah, L equal to 0, 3, 2. Yeah, that's positive. So it is okay, even simpler. Okay, z to the power 7.
All the terms are positive.
All the terms are positive. Okay. Yeah. So you just have to put the value and get it. Now, I'm going to do one more thing, and then I'll talk about what this is, the importance of all these things. L equal to 1. What is happening?
The second becomes 0.
The second becomes 0. Now the other one, this has become, y2 has become a polynomial, and this one is an infinite series now. Okay, so when this is the case, y1z, I'm going to now call it, I'm not going to expand it, but you can do it, some function of z. Okay, me now, infinite series, which is it's an infinite series. Okay, whereas y2z has become what? All the term goes away, and only the leading term is this. Okay. Maybe one more thing, maybe, which is y3z is other way around, right? L equal to 3. L equal to 3. Which one? Oh, L equal to 2. Sorry, I want to do that first. L equal to 2, because I also want to get normalized polynomial, so I can illustrate with that. L equal to 2, what happens is, this has terminated. Okay, one of the first solution becomes polynomial, and L equal to 2, right? 1 minus 2, 3, 2 square z square, okay? Or L equal to 2, right? I want to, okay. I want to also, maybe I'm tempted to introduce a notation, but I'll do it in a minute. So this is nothing but 1 minus 3z square, okay? And the second solution for L equal to 2, you can substitute that, but I'm just right now, I'm going to call it as some infinite series. Okay. So the first one, this is called Legendre polynomial of second kind, and this one, the first one is called Legendre polynomial. It is a polynomial, okay? The second one is called Legendre function because it's not a polynomial. It's an infinite series, so it will be called as Legendre function, okay? Now, in quantum mechanics, in electromagnetic theory, you will see these notations. This one will be written nothing but y1z is nothing but p naught, L equal to 0, right? I mean, this is called Legendre polynomial order 0, okay, p0. And this one is nothing but p1z, L equal to 1, okay? So one of the solutions of this Legendre polynomial differential is the Legendre polynomial PLZ for any L. The other one is an infinite series. That's how you write the most general solution. And this is nothing but P3Z, okay, L equal to, sorry, P2Z, okay. This is P2Z. This is the notation used. So this one, this subscript is nothing but the value of L, okay. One more thing, in quantum mechanics, you'll see this as not 1 minus 3z squared, but you'll see it as 3z squared minus 1 over 2 factorial, okay. That is because they have normalized the Legendre polynomial, okay.
Is the constant A1?
What did you say?
We take the constants 1 here.
Yeah, or each Legendre polynomial, each one will have this, right? What they say is P for any order L, Legendre polynomial, L equal to 0, 1 or 2, for z equal to 1, we must get value 1, okay? That's how we normalize the Legendre polynomial. So if you calculate this P2z the way it is for z equal to 1 is nothing but 1 minus 3, which is minus 2, okay? This is the value of this poly. The other case is trivial, so I'm not doing that. So the normalized Legendre polynomial, as you will see in some books, is P2z is normalized, will be written as 3. It's the same thing. Function form has not changed. It's just a factor of, it will be written as 3z squared minus 1 over 2 factorial. That's a form. If you open any book, the Legendre polynomial second order will be written like this, in this notation. Okay, P1z doesn't matter. P1z is z, we don't have to normalize. And P naught z is 1. Legendre polynomial order 0 is 1. Legendre polynomial order is, of L equal to 1, first order is z. Legendre polynomial of order 2 is this quantity, and so on and so forth. You know, you can get P3 by putting L equal to 3 and all that, okay? So these will become part of your excited states of your wave function, P naught, P1, P2. One will be part of a ground state, then one will be first excited state. So you need to know the way their behavior is different, right? P naught z as a function of z, PLZ, let me call this a function of z. First is a constant, P1z is a straight line, P2z is 3z squared minus 2 for z equal to 1, it's minus half. So it's something of this nature, okay? So that is P2z, and P3z will be, we can calculate it, but it will have a node at z equal to 0. So P3z is something. So each one has different functional form, okay? And that we understand, okay? But you can calculate that explicitly from here. So the most general solution of Legendre differential equation is then, can I say, it will have one part which is Legendre polynomial. I'm going to call some coefficient is there, okay, plus qz, okay. So this is an infinite series. regardless of L equal to odd or even, we know one series will terminate and become a polynomial. Okay, the value of that will change, and other one will be either this infinite series or that infinite series, depending on the value of L, it's odd or even. Okay, so in a way, what we can see is our Legendre differential equation the most general solution could be linear combination of these two. Okay, one is a polynomial, the other one is an infinite series. And I wrote infinite series for in some case. In this case was fairly simple. Calculate. You put L, whatever the value of L is, okay, and put that in that expression, and you will corresponding to L equal to 3, you will get on the 1. And so you really need most of the math physics book or quantum mechanics book or even EM electromagnetic theory book will have a table of P0, P1, P2, P3, all these things, P5. Up to that you will do that, and so it's not easy. Okay, so next time I'll talk about how about I'm not going to look at this infinite series to find out what is my P0, P1, P2, right? So we will develop other methods called generating function method, so that what I'll say is if I know P0 and P1, which is very simple, because P0 for any value of z is 1 and P1 for any value of z is z, knowing that, can I calculate P2, can I construct a recursion relationship between different quantum numbers of PL, right? I mean, that's what it, L is a quantum number basically eventually, right? It will become an arbitral momentum, angular momentum quantum number, something like that. Okay, so, but the origin of that is really coming from your Legendre differential equation. And what it says is, if L is an integer in your, it's not a real number, it's an integer, then one of the solutions will become a polynomial, and that polynomial is nothing but a Legendre polynomial. Okay, and it has certain values. Okay, meaning it will start, P0, P1, P2, P3. Each one of them you can tabulate basically. Okay, so that is what it is. So you should know this actually, at least the minimal properties, right? This has got linear behavior, okay? P2z is quadratic kind of a thing. P3z you can calculate, I will write down because it has got some cubic terms and all that, so I'll copy, but you can calculate from that expression that I have given you. It is, the second one will give the polynomial L equal to 3. You'll have this term and that term only. Okay, so that's what you'll have. The rest of them will become 0. So that's what will give you P3. Let me see if I have it. Yeah, I have it. That is normalized. All these things are normal. I'm going to put an N to say it's normalized, okay? Because if you just plug it, you will get a slightly different value. So just to remember its normalized value. Yeah, did you have any question? No. All right, so that's what, now that you know this is what we have to do for every differential equation. I mean, Bessel or Legendre, you can solve it, but each one will have different kind of infinite series. The form will be different because the PZ, QZ is different, or maybe you have to use Frobenius series rather than ordinary power series. And but you have the technique basically to calculate solutions. And what is interesting for us is eventually the properties of these functions. Okay, that's what is interesting because that's where the physics is embedded. Okay.
Dr. Jayanthy, so
Yeah.
if you know the Legendre polynomial of your solution,
Mm.
can you use the Wronski method to find the functional form of the infinite series of the second?
I'm going to come to that in a minute, okay? I'm going to give you a problem at this point. I mean, yeah. So basically, I'm going to, yes, let's do this in a way. Let's see, what was I going to do that? Okay, maybe let's do it this way, okay? Maybe do it for a simple case. Maybe I'll give you home like a more difficult problem. Okay, maybe I will do this, this problem, okay? Let's also not get confused of the notation P of Z here and the Legendre polynomial P, we have different things, it's got a subscript, okay? So maybe I'll do this and maybe can you try at home? Maybe the algebra there is more. Okay, if I give an equation like this, you should immediately say what is one of the solutions, okay? Huh? What is this? This is Legendre differential equation. So one of the solution is what?
Called Z.
No, you already given me that. Okay, P1Z, yeah, P1. Because L equal to
1.
L equal to 1, right? So P1Z is nothing but Z. So now that you know the solution of this without even doing anything, okay? It is P1Z, and P1Z is that. Here the solution is what? P naught Z. One of the solutions is Y1 Z is that. Here Y1Z is this, okay? The Wronskian is the same in both the cases, okay? But there is this differential equation of that, but the solution is going to be different, right? I mean, so yeah. So we can get the second solution by the Wronskian method, so which will be an infinite series which can be converted into a function because we have these things in a nice functional form, right? Y1Z is in a nice functional form, and as long as W is also nice, we should be able to get the infinite series can be written in a nice functional form. All right, so what is W here? What is Wronskian? So what is the Wronskian? What is P?
-2Z.
So P of Z is negative 2Z over 1 minus Z squared, right? Or Wronskian is nothing but exponential of negative 2Z over 1 minus Z prime squared dZ prime, this. And what is this? It's 2Z prime. Numerator is the differential of the denominator, so that is nothing but natural log of 1 minus Z squared, right? So WZ is nothing but exponential of negative natural log of 1 minus Z squared after you take the upper limit and all that, which is nothing but 1 over 1 minus Z squared. So this is my Wronskian. Okay, so the formula for calculating the second solution, if you knew the first solution is, the first solution Y1Z, Wronskian in the numerator divided by this first solution square in the denominator. since this is a constant, all we have is this is nothing but z, and wz was 1 over 1 minus z squared, and this is 1. Okay, so this is my second solution. All right, so what is that? Let me see, I don't know, let me check. This will be 1 minus z minus 1 plus z, right? That will cancel. See. No, this is plus there, right? Okay, I should look at it that way. 1 minus z, 1 plus z will be 2, that will cancel. Okay, good. That's what I need. All right, so I can separate them out like that, right? Half of 1 plus z, what's this, like this? Okay. I can separate that into 2 terms like this, right? I just did the partial fraction of 1 minus z squared. So it's 1 minus z plus half has to be here also, yeah. All right, natural log of 1 plus z, and here I will have negative natural log of half 1 minus z. So this is nothing but half of natural log of that will be our closed form, functional form of that infinite series, the one you asked whether I can write it in that. That's what it is, okay? But you can check whether, you know, you have that series. Let's go back and check whether it indeed is correct or not. That also we can do. Is this clear what I've written?
Yeah.
Okay. All right, so what is natural log of 1 plus z? You can check with the, you know, I want to confirm that if I put p naught equal to 1 in my infinite series, whether q of z becomes this, okay, solution. So whether it gives the same series or not, that we can also check. Okay, what is natural log of 1 plus z expansion? Natural log of 1 minus z, what's the expansion? There are certain functions we can write it in infinite series, and we should, they'll all become useful for us, okay? So this is nothing but z minus z squared over 2. So this alternates, and this one, all the terms are negative. It's not factorial, it is just, okay. So this function can be expanded into this infinite series, okay, main now. These you can find in, you know, some standard math book, okay, main now. So these things will come again and again, so I would encourage for you to remember some of these expansions, because, you know, yeah. So we have to subtract that, right? I mean, so what we have is natural log of 1 plus z minus natural log of 1 minus z.
Professor,
Yeah.
I think we should add.
Huh?
I think we should add the 2 terms.
What did you say?
I think we should add the 2 terms.
Add or subtract? Let's see. I made a mistake. Let's see. I had a negative sign. We are subtracting it, right?
That's correct.
We are subtracting it because we have this minus half is common, right? This is what we have to get.
But from the integral, you have the plus sign.
I have a negative sign here. When you have z is 1 minus z, is natural log of 1 minus z with a minus sign. This becomes a negative after integration.
Oh, okay.
So you have to remember that 1 minus z, you put it as under the variable z double prime or something, you will then have a negative sign because of that. So because this 1 minus z, natural log of, let's say 1 over z is natural log of z, but when you have 1 minus z prime, substitute into it on the variable y or whatever it is, and then you will have an effective negative sign here, okay, because of this, okay, I mean now you will get a negative sign, okay. All right, all right, so so we subtract that, so then we have so we have 2z plus 2z cubed over 3, you know, I think the next term will be 2 z to the power 5 over 5 and so on and so forth. Okay, and I have a half factor. So this series, if you go back and look at what we had derived, does it correspond to same series or not? Okay, I mean that is what you have to check. All right, because we had PL, remember we had y1z and y2z, and for L equal to 0, all the terms became 0 and became 1, and y2z, when for L equal to 0, are you getting this series? You can look at the series that I developed, and it should become that. Okay, so we're just checking from different ways, that's all. This is just to, this series says same as a functional form. Okay, so we couldn't have guessed it, you know, it would have been very hard for us to guess that was natural log of 1 plus z, right? But there's a functional form attached to that infinite series, and that functional form is this, okay? Okay, this is nothing but all right, I think we'll stop here today because I want to get started maybe next time on generating function method. So, and then maybe also give something called differential representation of the Legendre polynomials. What else do I want to, I mean, yeah, those things are important. Generating function method is also important. Eventually in quantum mechanics, we'll have normalization conditions, right? I mean, so all those properties of normalization properties of the Legendre polynomials will come out very nicely once I introduce the generating function method. Okay, so that's one other thing in quantum mechanics. You have to know what is the normalization condition for PLX, PMX. These are two different quantum numbers. It will be 0, but if it is not, what is it, and all that stuff. Okay, so all those properties will come very nicely by a different method called generating function method. You have some idea of series method now. I mean, we'll come back when we come to the Bessel function, but I want to go deeper into Legendre polynomial properties now. Okay, yeah, that's what I will do. Okay, yeah, all right. Any questions? I mean, did I go very fast or something? I mean, if there are any questions, let me know.
Check the homework. The first one is exactly the same.
Yeah.